సార్ నేను జాయిన్ అయ్యాను. పోనీ ఇద్దరే ఉన్నారు సార్, అంతేనా? ఇద్దరే కనపడుతున్నారు. మరి వాళ్ళు కూడా ఏం రెస్పాండ్ అవ్వట్లేదు. ఓకే, లైవ్ స్ట్రీమ్ కూడా అంటున్నారు కదా అని డౌట్ వచ్చింది నాకు. ఓకే సార్, నేను క్యారీ అయిపోనా, చెప్పేనా? వస్తుంది సార్, ఒక్క నిమిషం. ఓకే సార్, వస్తుంది. థ్యాంక్ యూ. Students, good afternoon. Is my screen visible? Hello?
Visible, madam. Good afternoon.
Yes, madam.
Yeah.
Good afternoon, madam.
Good afternoon. Dear students, I am Dr. K. Vijay Lakshmi. I am working as an associate professor at Loyola Academy, and I have more than 30 years of teaching experience. I have written books on abstract algebra, vector calculus, and also I am academic counselor at Ambedkar Open University. Now, today I am going to take commutative algebra. For this commutative algebra, we need some basic concepts of rings. So, just in these 8 classes, whatever the classes I'm going to take, we will divide and I will explain very important theorems of commutative algebra. But for anything, you need the basic concepts of rings, homomorphisms, isomorphisms, ideals, and prime ideals and maximal ideals. Without these concepts, we cannot go ahead with the commutative algebra. See here, we all of us know from abstract algebra what is a binary operation. What is a binary operation? We say that suppose you have G is any non-empty set. If G is any non-empty set, then we say that star is a binary operation. Star is a binary operation on the set G if A star B belongs to G for every A comma B belongs to G. This is also known as closure property. We say that the non-empty set G is said to be closed with respect to star if A star B belongs to G for every A comma B belongs to G. We know what is associative property. If for every A, B, C belongs to G, if A star B star C is equal to A star B star C, then we say that the binary operation star is associative. And we say that E is identity element. E is an identity element if A star E equal to E star A equal to A for every A belongs to G. Now, if for every A belongs to G, there exists B belongs to G such that A star B is equal to B star A is equal to E, then we say that E inverse of A exists, or we say that A inverse is B. For example, see here, if you consider Z the set of all integers, we know that A comma B belongs to Z, A plus B belongs to Z, because for any two integers A and B, sum of two integers is again an integer, and the addition is associative. A plus B plus C equal to A plus B plus C, and we know that 0 is the additive identity, and you have A plus 0 equal to 0 plus A equal to A for every A belongs to G, and you have for every A belongs to Z or G. G is the set of integers here. You have, or you can take A belongs to Z, there exists minus B belongs to Z such that minus A belongs to Z such that A plus minus A equal to A minus A plus A equal to 0. So one of the important examples of groups is set of integers, which is a group with respect to addition. And also in addition to that, you have A plus B equal to B plus A for every A comma B belongs to Z. So what do you mean? This property is known as commutative property. What is, when do you say that a binary composition is commutative? If A star B equal to B star A, then we say that star is commutative. So in the set of integers, addition is commutative. Now let us come to the main point. We say that suppose if you take G, any non-empty set equipped with one or more binary operations. A non-empty set G equipped with one or more binary operations is called a group if first one star is associative, and second one there exists E belongs to G such that A star E equal to E star A equal to A, and for every A belongs to G, there exists B belongs to G such that A star B equal to B star A equal to E. That is, inverse exists for each and every element. Then we say that G with respect to star is called a group. In addition to that, if binary composition is commutative, that is, if A star B equal to B star A, then group G is said to be a abelian group. It's said to be an abelian or a commutative it is an abelian group or a commutative. I think students, all of you have knowledge of groups. Hello? All of you know what is
Yes,
a
ma'am.
group? Yeah?
Yes, madam.
Yeah. So now this is a group. Now we are we are going to discuss about rings. So a non-empty set, because everybody knows about groups, that's why I'm not focusing much on rings. And so here, what is a ring? Ring is an algebraic structure R plus dot. R plus dot is called a ring if, see here, more than abstract algebra is the study of dissimilar objects or similarities between dissimilar objects. More than almost all abstract algebras. What do you mean by this abstract algebra? Abstract algebra is the study of similarities between dissimilar objects. So that is the reason we start with a non-empty set. In that, we define a binary composition. We know addition is a binary composition. Multiplication is a binary composition. We know how to prove it is a group and all. So what will happen? Is it necessary for any non-empty set to have only one binary operation? No, any set can have more than one binary compositions. See, for example, suppose if the number of elements in G is n and 4. What is the number of elements in G into G? It is n square. So what is a binary operation? In fact, binary operation is a mapping from G into G to G. So there exists n to the power of n square binary operations. There exists n to the power of n square binary operations on a non-empty set. So in rings, we are going to study about two binary compositions. A non-empty set R equipped with two binary compositions, addition and multiplication, is called a ring if first one, R plus is an abelian group. R plus is an abelian group. And second one is R dot is a semi-group. R plus is an abelian group. R dot is a semi-group. And third one, distributive laws are satisfied. That is, you have A into B plus C is equal to A into B plus A into C. Or you have B plus C into A is equal to B into A plus C into A. These are called distributive laws, or we can say that addition is distributive over multiplication. Addition is distributive over multiplication. So now here, some cases will arise. I'm saying that if R is any non-empty set, R plus is an abelian group, R dot is a semi-group. Semi-group means anybody can tell what is a semi-group, Amma? Semi-group is the one in which binary composition is associative. Okay. Now, in addition to this, you have the second binary composition, multiplication. A into B equal to B into A. Then we say that R is a commutative ring. R is a commutative ring. If identity element, multiplicative identity, one belongs to R, then we say that R is a ring with unity. R is a ring with unity. And for every non-zero element in R, if 0 not equal to A in R, there exists B belongs to R such that A into B equal to 1, which is the same as B into A. Then we say that B is the multiplicative inverse of A. B is the multiplicative inverse of A. So we say that a commutative ring with unity, a commutative ring with unity is called a field if every non-zero element possesses inverse. Okay, we can talk about commutative ring with unity is called a field if every non-zero element possesses multiplicative inverse. We can say that multiplicative inverse. It is called a field. Now, see here, if there exists B such that A into B equal to 1, then we say that the B is also called unit element in the ring. It is a unit element in the ring. There is a lot of difference between unit and unity element. Now here, what do you mean by zero divisors? See here, suppose R is a ring. See here, ma, 3 into 2 under modulo 6. What is this value? What is the 3 into 2 under modulo 6? Students, 3 into 2 under modulo 6 is 3 2s are 6. 3 into 2 is 6. 6 when divided by 6 will leave the remainder 0. That is, the product of two non-zero elements is 0. So we say that R has no zero divisors. R has no zero divisors. If AB equal to 0 implies either A equal to 0 or B equal to 0. What do you mean by zero divisors? Zero divisors means A not equal to 0, B not equal to 0. Then AB is 0 means this is called the zero divisor. We say that R is without zero divisors if and only if AB equal to 0 implies either A equal to 0 or B equal to 0. Now we know that in a ring R, cancellation laws holds good. In a ring or cancellation laws holds if and only if R is without zero divisors or R has no zero divisors. How you prove? What do you mean by cancellation law, Nana? See here, suppose you have A not equal to 0, AB equal to AC. AB equal to AC implies A into B minus C equal to 0. This implies B minus C equal to 0. Because why? Suppose R has no zero divisors and R has no zero divisors. Means A not equal to 0 implies B minus C must be 0. What do you mean by R has no zero divisors? The product of two numbers is 0 only when one of them is 0. The product of any two numbers is 0 only when one of them is 0. Suppose you have a into b minus c equal to 0 and a not equal to 0 means what does it imply? You must have b minus c equal to 0. b minus c equal to 0. What do you mean by that? This is b equal to c. That is cancellation law. AB equal to AC implies B equal to C. Whenever the ring R has no 0 divisors, then it satisfies cancellation law. Similarly, we can prove BA equal to CA implies B equal to C. Here you are applying cancelling left-hand side element. So it is known as left cancellation law. What do you mean by cancellation law? AB equal to AC implies B equal to C. Similarly, BA equal to CA implies B equal to C. This is known as right cancellation law. So whenever the ring has no 0 divisors, then the cancellation law holds, and whenever cancellation law holds, the left, whenever cancellation law holds, definitely it satisfies R has no 0 divisors. Suppose, see here, you have suppose AB equal to 0. We want to prove that R has no 0 divisors whenever cancellation law holds. So suppose AB equal to 0. What you have to prove? We have to prove either A equal to 0 or B equal to 0. So this implies AB equal to A into AB equal to 0 means you can write AB can be written as A into 0. Because you assumed that cancellation law holds, you get B equal to 0. What do you mean? Whenever cancellation law holds, you have AB equal to 0 and A not equal to 0 implies B equal to 0. Suppose if B not equal to 0, then A must be 0. So this is the important point you have to remember. What it is? R has no 0 divisors if and only if cancellation law holds. A commutative ring with unity in which each non-zero element has multiplicative inverse is known as a field. And after that, see here, I think students, you have all done rings in degree. Students, all of you have, do you have an idea of rings? Hello, students, are you listening?
Yes, madam.
Yeah. Just, am I teaching fast? Hello?
No, madam. No.
Yeah. Just today you will have only introduction class. From tomorrow onwards, I'll give you the all important theorem, explanation of important theorem, because without these concepts, we cannot move further. And next one is a field has see here, one more thing. I want to give one more definition before doing this problem. Suppose a commutative ring with unity, a commutative ring with unity that has no 0 divisors is called an integral domain. A commutative ring with unity that has no 0 divisors is called an integral domain. Integral domains play a very important role in this commutative algebra. This commutative algebra basically contains analytical and topological concepts of algebra. Okay, we are going to have modules and we are going to have radicals. Okay, and the Artinian theorems and more you have to focus on homomorphisms. What do you mean by a homomorphism? So the concept of functions is very, very important. Whenever it comes, I'll give the basic definitions also. Now, a commutative ring with unity that has no zero divisors is called an integral domain. Immediately, what does it follow? Every field is an integral domain. Every field is an integral domain. Why every field is an integral domain? Because, tell me, see here, if you want to learn abstract algebra, any algebra means focus on definitions. Focus on definitions, what is given and what you have to prove. Students, in these 8 classes, I divided 2 chapters for each session. So today and tomorrow, I will finish first and second sessions of commutative algebra. Kindly don't miss class tomorrow, because I am going to explain important theorems from 1 and 2 chapters, because total you have 18 chapters and 9 classes means we focus on very important concepts of commutative algebra. So why you call every field is an integral domain? Suppose F is a field. What do you mean by F is a field? F is a commutative ring. If F is a field, then F is a commutative ring with unity that has no zero divisors. That has no zero commutative ring with unity F is a field means F is a commutative ring with unity in which each non-zero element possesses multiplicative inverse.
Madam, your screen is not visible, madam. Your screen not visible, madam.
Screen is not visible.
మీరు రాసేది కనపడట్లేదు మేడం.
ఓన్లీ వైట్ బోర్డ్ కనిపిస్తోందా?
అసలు కనపడట్లేదు మేడం.
ఓకే, 1 minute అమ్మా. Till now it was visible, no ma? Last 10 minutes it is visible, no?
నో మేడం, మీరే కనిపిస్తున్నారు.
Now?
ఇప్పుడు కనిపిస్తుంది.
Okay. Okay, it should come like this. Okay. So every field is an integral domain. So F is a commutative ring with unity in which each non-zero element possesses multiplicative inverse. That means if 0 not equal to A belongs to F, then you have A inverse belongs to F and A into A inverse is equal to A inverse A equal to 1. Okay, now you have, suppose what is required to prove? You have to prove that a field has no zero divisors. Always analyze 2 things. What is given, what you have to prove. What is given and what you have to prove. Now here, given that F is a field and you are asking to prove that F is an integral domain, what is the point missing in field and integral domain? The integral domain is a commutative ring with unity that has no zero divisors. Field is a commutative ring with unity in which each non-zero element possesses multiplicative inverse. So this third point is missing for the integral domain or field. Only third point is the difference. Okay, so that is the reason. In order to prove that a field is an integral domain, we prove that field has no zero divisors. It has no zero divisors. We prove that field has no zero divisors. For that, take A B equal to 0 and A not equal to 0. Whenever A not equal to 0, you have A inverse belongs to F and A inverse AB equal to A inverse into 0, which is 0. This implies 1 into B is 0. This implies B equal to 0. Students, screen visible now?
Yes, madam.
Yes. See, all this time for the last half an hour, it is not visible. Hello?
Yes, madam.
Oh. Okay, immediately you tell me, Amma, whenever it is screen is not visible. I thought I'm writing on the screen and telling, Amma.
Okay, madam.
Okay, no issues. So whenever B not equal to A not equal to 0, AB equal to 0 and A not equal to 0, we are able to prove B equal to 0. Similarly, whenever B not equal to 0 and AB is 0, we can prove A equal to 0. So that is the reason field has no zero divisors. So every field is an integral domain. Every field is an integral domain. But integral domain need not be a field, but integral domain need not be a field. Why? Because you see here, suppose if you take Z, the set of all integers like -4, -3, -2, -1, 0, 1, 2, 3, and so on. If you take a set of all integers with respect to addition, we know that Z plus is a abelian group. Z plus is an abelian group. And we know that Z dot is a semi-group. And you have Z dot is a semi-group. And also you have distributive laws with respect to addition. You have A plus B, A into B plus C is equal to A into B plus A into C, B plus C into A equal to B into A plus C into A. So distributive laws are also satisfied, and also multiplication is commutative in the set of all integers, and also 1 belongs to Z. But only the problem is any non-zero element other than 1, it has no multiplicative inverse. In the set of integers, there is no multiplicative inverse. That is, for every A belongs to Z, there is no 1 by A, such that A into 1 by A is 1. So that is the reason Z is not a field. So I told you, every field is an integral domain, but integral domain need not be a field. This is the example. Z is the example for integral domain, which is not a field. Now, students, let us come for subrings. What do you mean by subring? Suppose you have R is a ring. And S is any subset of R. R is a ring. S is any subset of R. That is, all the elements of S are also the elements of R. So we say that a non-empty subset, S of ring R is said to be a subring of R, is said to be a subring of R if S itself is a ring. If S itself is a ring, a non-empty subset S of ring R is said to be a subring of R if S itself is a ring. That means S is a Boolean group with respect to addition, and S dot is a semi-group, and distributive laws are satisfied. But every time, if you want to prove any subset of ring R as a subring, no need to verify all these properties. So what we will do, we say that a non-empty subset S is a subring of ring R if and only if first one A comma B belongs to S implies A minus B belongs to S. Second one, A comma B belongs to S implies AB belongs to S. S is a subring of ring R if and only if A comma B belongs to S implies A minus B belongs to S, and A comma B belongs to S implies AB belongs to S. So this is called subring. Similarly, subfield and suppose if F is any field, students, if you have any notes related to this ring theory, kindly go through it so that commutative algebra you can easily understand. Okay. Suppose F is any field and K is any non-empty subset of F. Then what we can say, F is K is a subfield if and only if A comma B belongs to K implies AB inverse belongs to K, and A comma B belongs to K implies A minus B belongs to K. So this is about subsets. And also always you have to remember that the union of C, the union, suppose S1 and S2 or any two subrings, any two subrings of ring R, then S1 intersection S2 is always a subring. Then S1 intersection S2 is always a subring, but S1 union S2 is not a subring. But S1 union S2 is a subring if and only if either S1 is contained in S2 or S2 is contained in S. Okay, and even for the fields also same thing will happen. And the next one is, next important concept is after the subrings. Next, let us define a special kind of ring called a Boolean ring. A ring R is said to be a Boolean ring. A Boolean ring if A square equal to A for every A belongs to R. Student, can you tell the name? What is the special name if A square equal to A? Anybody knows? What do you mean by A square is A?
Prime.
Yeah? A is an idempotent
Identity.
element. Yeah. We say that A is an idempotent element in R if A square equal to A for every A belongs to R. Ma, students, are you comfortable with my teaching?
Yes, madam.
Yeah, okay, ma. You have any doubts, means Just simply send a message, I'll know here. Okay.
Okay.
Okay, ma'am.
Anytime screen is not visible. Generally, I'm writing on the digital pad. It will coming on the, whenever I am writing, it is coming on the screen. And so if at all it is not visible means inform me immediately. Now, Boolean ring. What do you mean by Boolean ring? If all the elements are idempotent elements. So can you have some properties of Boolean ring? Just let us do one theorem on Boolean ring. Whenever R is a Boolean ring, then first one, always you have A plus A is 0. Second one, whenever you have A plus B is 0, then you have A equal to B. And third one, you have AB equal to BA. That is a Boolean ring, always commutative ring. There is no second thought among. Every Boolean ring is a commutative ring. Whatever the properties that are satisfied by commutative rings, it is satisfied by those properties will be satisfied by these Boolean rings. How you prove? First one, you have to prove A plus A equal to 0. For this, tell me, Amma, students, if A square is A, for every A belongs to R, tell me what is A plus A whole square, student?
A.
A square plus 2A square plus A square.
No. See here. If A belongs to R means you have A plus A belongs to R. Treat this as a single element. Now you tell me, if A square is A, then what is A plus A whole square?
2A.
A plus A.
Yeah, very good. A plus A. Because you treat this as a single element. A plus A whole square is A plus A only.
A plus
But
A.
according to our theory, what you told is correct. Just now you told what is A plus A whole square? This is A plus A into A plus A, which is A plus A, which
Yeah.
implies distributive law. Apply distributive law. A into A plus A. Again plus A
A
into
into A plus
plus
A
A.
into A.
So this is nothing but A square plus A square. Again plus A square plus A square is A plus A. Tell me what is A square again? A only. So
A.
A plus A again plus A plus A is equal to A plus
A
A
plus A.
plus 0 raskondi. You can apply left cancellation law so that you get A plus A is.
A equal to
A
0.
equals to 0.
So in a Boolean ring, A plus A is 0. Because this result we are going to use in commutative algebra at several places. Okay. Now, you have to prove, just now, second one. A plus B is 0.
0.
Students, what is the 0 now? A plus B is A plus A. Just
plus
now
A.
we proved that A plus A is 0.
Yes.
So by left cancellation law, B equal to A.
B equals to A.
So what do you mean by A plus B equal to 0? A plus B equal to 0 implies A equal to B.
B.
And third one, we have to prove it is commutative. So because R is a ring, for every A comma B belongs to R, by closure property of addition, you will get A plus B belongs to R. Now tell me what is A plus B whole square? In a Boolean ring, tell me
A plus
what is.
A plus B.
Yes. A plus B whole square is A plus B.
A plus B.
Again, A plus B whole square is A plus B into A
A
plus
plus
B.
B
Equal to A plus B.
equals to A plus B.
Student number. A into A plus B plus B into A plus
A
A
B
plus B.
equal to A plus B. This implies A square
A
plus
square
A
plus
square
AB.
plus AB
A
plus
B
BA
plus
plus B square
A
equals
plus.
to A plus B.
Again, tell me what is A square? A only.
A
A plus AB
plus
plus
B.
BA
A
plus
plus.
B equals to A plus B.
So you can apply left cancellation law now. That is the reason I told you in the beginning itself. In a ring, R has no zero divisors means it satisfies cancellation laws. So
Laws.
here Boolean ring annam kadandi. Ring in ring, it has no zero divisors. So you take left cancellation law, right cancellation law. If you apply, you get AB plus
AB
BA
plus
is
B
zero.
equals to
Now
0.
just now we proved whenever in a Boolean ring A plus B equal to 0 implies A equal to B.
B.
Therefore, AB plus BA equal to 0 implies AB equal to
BA.
So what do you mean? A Boolean ring is always a commutative ring. So this is one of the, see here, if A square is A, we are calling it as a Boolean ring. Okay. Suppose there are some elements. Why you have to take A square? You can take sometimes A cube is A. We have seen many matrices, matrix product. There are some matrices whose cube is A. Got my point? So like that, you can have A power P also A in general.
A.
So this kind of rings are called P rings. So tomorrow we will study the properties of P rings. Just today, I have to give some introduction about these Boolean rings. Okay, ma. Next one, next concept is. So this is about Boolean ring. If A square is A, it is a Boolean ring. Suppose if A power P is A, it is a P ring. Okay. Next one, I'm going to talk about ideals. Ideals. What do you mean by an ideal? Okay. See here, we say that a non-empty subset S of R is said to be an ideal. That we can say we can say any non-empty set A is any non-empty subset A of R is called an ideal. If first one A minus B belongs to A for every A comma B belongs to A, and the second one R belongs to R, A belongs to A, implies RA belongs to A and AR belongs to A. What do you mean by RA belongs to A? Suppose if you take ring element left hand side, element of A in right hand side, if ring element is on the left hand side and RA belongs to A, implies A is left ideal. And AR belongs to A and A minus B, this will be there always. Okay. If AR belongs to A, we say that A is right ideal. If a ring is a commutative ring, if R is a commutative ring with unity, then there is no difference between a left ideal and right ideal. Okay. Left ideal and right ideal. Now here, next one is principal ideal. What is a principal ideal? An ideal A of R is said to be a principal ideal if capital A is contains set of all elements of the form RA such that, okay, small r, RA such that R belongs to R. That is, it contains multiples of elements. So if every ideal of a ring is a principal ideal, it is known as principal ideal ring. It is a principal ideal ring. So what do you mean by, see, suppose if you just let me give one example for this. Suppose consider the set RA and RA is equal to the set of all small RA such that R belongs to R. Then I prove that RA is an ideal. What is a capital R? R is a commutative ring. Don't take ordinary ring. Generally, throughout this commutative algebra, we take R as a commutative ring. We restrict ourselves to commutative rings. So you take R1 comma R2 belongs to R. Then you have R1A belongs to capital RA, R2A belongs to capital R into A. Then you will have R1A minus R2A, which is R1 minus R2 into A. Why? Because ring satisfies distributive property. Because ring satisfies the distributive property, we can say that R1A minus R2A equal to R1 minus R2 into A, which belongs to capital R into A. That means, what do you mean? RA is a subring. RA is a subring with respect to addition. Now you have, let R belongs to R and R1A belongs to capital RA. Then tell me, what is R into R1A? It is R1A, which belongs to RA, because R is closed with respect to multiplication. Because R is closed with respect to multiplication. If R is a commutative ring, then you can write RR1 is equal to, see, tell me, what is AR1? You take A, R belongs to R1. Okay. No, you take like this, R into AR1. This is nothing but, because ring is commutative, AR1 can be written as R1A.
R1A.
Yeah, RR1
Into R1A
belongs to
RA.
Yeah. So you have RA. RA is the set of all elements of the form RA such that R belongs to R is an ideal. Always this is an ideal. The multiples of all elements of these ideals, this is also known as principal ideal. Principal ideal generated by A. How you write? If A is the ideal generated by A, means we write A is generated by A. So if every ideal is a principal ideal, it is known as principal ideal ring. So you have Z plus dot is a hello. Okay. Z plus dot is a principal ideal ring. Next one is coming to all of you. Do you have an idea of quotient ring? Suppose if S is an ideal, then we construct. One minute. Hello? Is my voice clear?
No, ma'am.
No, ma'am.
1 minute.
Oh, madam. Voice is
Some
cracked.
Yeah,
disturbance.
1 minute, 1 minute. Yeah, 1. Now is the screen visible?
Visible.
No, madam.
No. 1 minute. Now?
Yes, madam.
Yeah. See here, actually you have not seen from the beginning, no? I started with the binary composition and I have defined the group and then rings. Subrings, subfields, ideals, Boolean rings. All these are very important concepts to learn commutative algebra. So you have Z plus dot is a principal ideal ring. Now suppose S is an ideal. Then we can talk about R by S contains the set of all ideals. Okay. R plus S such that R belongs to R. And with respect to addition and multiplication, cosets, how you define a coset? Let us have some idea about cosets. Suppose if S is any subring, then S plus A, which contains elements of the form small s plus A, such that S belongs to S, is called a right coset. Generally, with respect to addition, ring is a commutative. Ring is commutative. So that is the reason simply we call it as a coset. Now you have S plus A equal to S plus B if and only if A minus B belongs to S. Okay. And also you have S plus A equal to S plus B implies you have fund only if you have A minus B belongs to S. We define addition of two cosets S plus A plus S plus B as S plus
S
A
plus
plus B.
A plus B.
Similarly, S plus A into S plus B as S plus AB. With respect to addition of these cosets, with respect to addition and multiplication of these cosets, you can say that, and these two are well-defined operations. Addition of cosets and multiplication of cosets is well-defined operations, and you have R by S is a ring, which is called a quotient ring or a factor ring. Okay. Now see here, after this, I'm going to define two types of ideals, namely maximal ideal and prime ideal. Maximal ideal and prime ideal. What do you mean by maximal ideal? The name itself, it says that it is the maximum of all the ideals in a ring R. Suppose R is a commutative ring and we say that an ideal A is maximal. An ideal A is maximal if there exists an ideal B such that A is a subset of B is a subset of R. That means there is no ideal between A and R. Suppose we say that A is a maximal ideal. An ideal A is said to be a maximal ideal. If there exists an ideal B such that A is a subset of B is a subset of R, implies either A equal to B or B equal to R. That means there is no ideal between A and R. See here, you have to remember one point. Every ring possesses two ideals, 0 ring and 1 unity ring. These two are called improper ideals of ring R. Any ideals other than these two are known as proper ideals. And we say that field has no proper ideals. Why? The only ideals of field are set containing 0 element and F itself. Every ring possesses two ideals, namely the set ring R itself and ideal containing 0. So other than these two ideals are called proper ideals, and these two ideals are called improper ideals. The only ideals of field are 0 and F itself. So a field has no proper ideals. And also you have R by S is a field if and only if S is a maximal ideal. The quotient ring R by S is a field if and only if S is a maximal ideal. Once again, definition of maximal ideal is if there is no ideal between A is an ideal of R and R is ring. There is no ideal between A and R. So how you define mathematically maximal ideal? An ideal A is said to be maximal ideal if there is any ideal between A and R, then either A equal to B or B equal to R. So therefore, we can say that R by S is a field if and only if S is a maximal ideal. And the next important concept is prime ideal. Students, any doubt in the concept of ideal?
No, ma'am.
Okay. An ideal S is called a prime ideal if AB belongs to S, implies either A belongs to S or B belongs to S. We say that an ideal S is said to be a prime ideal if AB belongs to S, implies either A belongs to S or B belongs to S. And we say that R by S is an integral domain if and only if S is a prime ideal. S is a prime ideal, then we say that R by S is an integral domain. So these are the important concepts of rings. So as a summary, what we learned today is a ring. First, we focused on the binary operation. We say that an algebraic structure G with a star is said to be a group if star is associative and there exists identity element, there exists inverse. Now coming to rings, a non-empty set R is said to be a ring if it is an abelian group with respect to addition. It is a semi-group with respect to multiplication, and distributive laws are satisfied.
Satisfied.
In addition to this, it satisfies the commutative property. This is a commutative ring. If it contains multiplicative identity, it is a ring with unity. So a commutative ring with unity, all these definitions, daily once you have to revise. Otherwise, we cannot prove theorems from commutative algebra. A commutative ring with unity is called a field if each non-zero element possesses inverse. A commutative ring with unity is called an integral domain. Integral domain means it has no zero divisors. A commutative ring with unity has no zero divisors, then it is called an integral domain. Now, next one, what is an ideal? Ideal is the one which is a subring. First of all, a non-empty set A is called an ideal.
If A minus B belongs to
A,
for all AB belongs to A.
A. For all A comma P belongs to A. And
A.
you have
And
RA belongs to A. That means C. That's
A
what
also
you
belongs
see.
to A.
A means ideal. Ideal absorbs elements from the ring. Okay. If R is an element of ring, A is an element of A, then you have RA belongs to A. That means A absorbs elements from the ring R. So this is an ideal. Immediately, actually, after defining ideal, the important result what you have to do is, see here, suppose you have R is a ring. R is a ring with unity. Now, see all the elements of A are elements of ring R. But there are some elements of ring which are not in A. Am I true? No, now you have R is a ring with unity and this one belongs to ideal. R, anyhow, one is in R. Suppose if one is a common element for A and R, then there is no difference between A and R and your A will become R. Students got my point?
Yes, ma'am.
R is a ring with unity. And one belongs to A. Then you have A equal to R. Why? Because as an ideal, A is a subset of R. First of all, A is subset of R always. Now you have to prove that suppose you take some A belongs to R. Then by closure property you have A belongs to R. One belongs to A. Suppose if I am saying that one belongs to A. Now by absorption property you have A belongs to A also. Got my point? A belongs to ring and one belongs to A. Implies A into one belongs to A. Because A is an ideal, no? It takes elements from the ring. It absorbs elements from the ring. So what do you mean by that? A belongs to R implies A belongs to A means R is a subset of A. So therefore A equal to R. So throughout these sessions, you have to remember that if R is a ring with unity and one belongs to A, then A equal to R. This is very important result. Now, next coming to integral domains and whenever this prime ideal, maximal ideal comes, theorems comes, I will explain with the examples also. Now, next concept is homomorphisms. Just this class, only I am revising the sessions, whatever you have learned from rings. Students, anyone can define homomorphism? Suppose
1, 1 and 2.
from a ring R into ring S. F is a function from a ring R to ring S. Then we say that F is a homomorphism if F preserves the binary operations in both R and S. What do you mean by F preserves the binary operations? That means you have F of A plus B is equal to F of A plus
F of B.
and F of AB is equal to f of
F of
A
A into F of
f
B.
of B.
F of B.
Every A comma B belongs to R. Okay. Now, suppose in addition to this 1, 1 function, suppose if f is 1, 1 and f is onto and f is homomorphism, then we say that f is an isomorphism. F is
Isomorph.
f is a 1, 1 and onto function. Just 1 minute. One minute. Internet is not working. Wait. Yes. Yeah. Whiteboard I am screen sharing. So we say that f is a homomorphism from a ring R onto ring S. If f of A plus B is equal to f of A plus f of B and f of AB equal to f of A into f of B. Okay, 1 minute. Students, is my screen is visible?
Yeah.
Because in between some internet problem.
Network problem.
Okay, f is 1, 1, f is onto, and f is homomorphism, means we call f is an isomorphism. What do you mean by 1, 1 function? Suppose if you have f is a function from a set A to set B, then we say that f is 1, 1. If distinct elements in A has distinct images in B. Students, f of A1 equal to f of A2 implies A1 equal to A2. There are many theorems based on this isomorphism problem. Isomorphism. See here, go through these concepts. Very, very important. What do you mean by homomorphism? Homomorphism preserves the binary operations, addition and multiplication. 1-1 function means distinct elements has distinct images. And we say that the function f is onto, if for every b belongs to b, there exists a belongs to a, such that f of a equal to b. That means corresponding to every element in the range, you can find three image in the domain. That means this is possible if and only if f of a equal to b. Now here, a 1-1 homomorphism is known to be a monomorphism. A 1-1 homomorphism is called monomorphism. Onto homomorphism is called epimorphism. Onto homomorphism is called epimorphism. A homomorphism from a ring R into itself, R to R. Instead of taking two rings R and S, if you take only one ring, F from R to R, okay, then it is called an endomorphism. Endomorphism means a homomorphism from a ring onto itself is called an endomorphism. An isomorphism from a ring or into itself is called automorphism. Okay, students, from your commutative algebra material for tomorrow class, come prepared with all the first chapter concepts. These are the introductory concepts which are given in chapter 1. Tomorrow we will do chapter 2 and 3. Actually, I am going to give you the definitions and important theorems. You can ask me any doubts now. Any doubts? Hello, any doubts?
No, ma'am. No.
No, ma'am.
Okay.
No, ma'am.
So tomorrow we'll see you at 1:30. Okay.
Okay, thank you, madam.
Okay.
Thank you, madam.
You are
Thank you.
welcome.